Nayak has had a very distinguished research career in condensed matter physics, particularly its topological aspects. And for the past several years, he's led Microsoft's effort to build a topological quantum computer. And, we're very privileged to have him today as a speaker. And so without further ado, I would like to request Professor Nayak to give his talk. Just to let you know, Professor Nayak, that the talk is approximately for 50 minutes. Okay, so now, I would like to request you to give your talk.
Pleasure. Thank you very much. Thank you for the invitation. Please feel free to interrupt and ask questions. If I don't see a hand raised, then someone please speak up. So, our goal is to build a topological quantum computer. An important piece of that is the processor, and it requires a couple of things. I'm going to give you this outline right now. This may not all make sense at this point, but I wanted to set this outline out now just so that it's clear where we're going with this. And if you want a quick outline, this is it. But I will explain all the things that I'm discussing here. So, and this is sort of what we've accomplished so far, and it'll give you a little bit. And I will wrap up by saying, where the road ahead takes us. So first of all, we have to tune a device into the topological phase with high confidence. If you want a topological quantum computer, you have to actually, this is based on a new phase of matter. You have to tune into the topological phase with high confidence. That's what the topological gap protocol is all about. And, we've shown that we can pass that with our devices. We then need to be able to measure topological charge, which is an emergent charge in topological phases of matter, or these are emergent quantum numbers. It turns out that fermion parity is an example of a topological charge in certain phases of matter, and we've shown that we can actually measure it accurately and quickly. We then need to be able to fabricate and control a complex device that has multiple anyons, which in our case is Majorana and zero modes, and in a way that we can control them so that we have a qubit. So we can store and process quantum information. And in our approach, which is often called measurement-based or measurement-only topological quantum computation, what we do is a sequence of measurements, and that includes natively different types of measurements like X and Z measurements, multiple non-commuting measurements. Another thing that I'll show that we've demonstrated. Now, to explain the context and what that's all about, the basic motivating concept behind topological qubits is that you can get a level of hardware-based error protection that is controlled by an energy scale, which is the topological gap. And infidelities, error rates, and infidelities in gates will be exponentially small in that scale, provided you're in a topological phase and that scale is large. So the footprint will be small, inversely proportional to that energy scale. The gate times, or how fast you can operate, the speed limit, will be small, inversely proportional to that energy scale. As I said, the error rates will be small. And also an additional interesting piece is that the operations are inherently discrete in a topological phase. So, the idea is that there are states of matter, and that's what topological phases are, in which the underlying quantum wave function has topological properties similar to how a Möbius band can be distinguished by its twist from an ordinary band. Similarly, some quantum states have such twists inherent in them that that actually protect them, because the Möbius band, even if you stretch on it or pull on it or crumple it up, as long as you don't tear it, actually the number of twists is extremely robust and is preserved. And it's that type of rigidity that one exploits in topological quantum computing. Now, of course, in an ideal world, that energy scale would be extremely large and we would never have to worry about errors. But in reality, it's going to be finite, and the temperature is going to be finite, and the size of the device is going to be finite. And so, our goal initially is we want error rates less than 10 to the minus fourth, length scale less than about 10 microns, and operation time less than a microsecond. And in that regime, we can, on top of it, do some software level error correction, and we can, really effectively run quantum algorithms to solve extremely valuable, interesting problems on a time scale of weeks to months rather than years to centuries. The particular phase of matter that topological phase that we're using. So, the idea is great in general, but of course you have to have a topological phase of matter. The one that we've been focusing on is topological superconductivity in superconductor semiconductor nanowires. Here, we take a semiconducting nanowire, and there's a superconductor layer on top of it. And as a result of the superconducting layer, some superconductivity gets induced through a barrier. And as a result, if we look at a very simplified model, the Hamiltonian is in the bottom left-hand corner. In the top right, you see the band structure for the bottom of the conduction band, and it has certain properties. One, we want a semiconductor that has large spin-orbit coupling, as a result of which that band structure gets split into two helicities by the spin-orbit coupling. And for us, large is larger than about 4 MeV nanometers. We apply a magnetic field, and we want along the wire, and we want the G factor to be very large, because with a large G factor, we get a relatively small magnetic field can open up a gap, a Zeeman gap, in the semiconductor at zero momentum. And by relatively small, I mean small enough that it doesn't substantially disrupt the superconductivity. Then we want good control over the density, which is, of course, the great property of semiconductors, that you can control the density well, so that we can put the chemical potential in that gap where there's only 2 Fermi points. And when that's the case, if we have a good interface with the superconductor to induce superconductivity uniformly and with the right magnitude, then the type of superconductivity we get is, in fact, topological superconductivity. Okay. And the way we get it is, for instance, by increasing magnetic field, we go through a phase transition from the trivial phase into the topological phase. The trivial phase in blue, that's kind of the ordinary superconducting phase that you would get with, say, aluminum or a typical low temperature ordinary superconductor. And the topological phase is what the system goes into at high magnetic fields. Now, what makes it more complicated is of course, that real materials have disorder. They are never perfect, never perfectly crystalline. They never have perfectly sharp and clean interfaces. And as a result of disorder, as the disorder increases, what happens is that topological phase breaks into smaller, it fractures into smaller pieces and moves to higher magnetic field and higher density, and eventually will actually disappear altogether if the disorder gets too strong. So disorder really is the main complicating factor here that makes it difficult to see the topological phase. To understand how much disorder you can tolerate, well, that depends a lot on exactly the growth and fabrication strategy. We've been taking one in which everything is based around indium arsenide quantum wells, so high mobility indium arsenide quantum wells. We then have a superconductor that's aluminum. It's a narrow aluminum strip. And then we have gates, electrostatic gates, which through their electric fields define the wire. So the wire is not grown as a wire like so-called VLS or vapor liquid solid nanowires. It is not etched from a 2DEG down to a nanowire. It's actually created by electric fields. It's a gate-defined nanowire. Okay, and for such a wire, and for any such system, for any one-dimensional topological, in order to get topological superconductivity in a nanowire, what you need is a localization length, okay, or basically roughly the mean free path. Since it's a one-dimensional system, the localization length needs to be larger than the coherence length. The localization length needs to be larger than the size of the Cooper pairs, okay? And for the kind of nanowire that I described, this gate-defined nanowire on a two-dimensional electron gas or on a quantum well, you need the quantum well itself, the underlying quantum well, to be very high quality. And that starts with a near-surface quantum well with high mobility and high mobility density slope. And what you can see is that we've accomplished this. This is data from an actual quantum well with a mobility density slope in excess of 100,000. So that's a factor of 3 to 4 above what the state of the art was when we started. We also need very high quality wires. Okay, what you can see here is going from bottom to top, the types of improvements we made in fabrication of these wires, you can see the line edge roughness and the quality of the aluminum wire improved over time. Because if that's not very high quality, then you'll have an additional source of disorder that will destroy the topological phase. We have a very high quality superconductor semiconductor interface. You can see a cross-sectional TEM at the bottom of one of our wires. You have a zoom in at the top, and you can see how very pristine that interface looks, and how well, how good the crystallinity is of both the, in this case, the indium aluminum arsenide as a barrier layer and the aluminum. And then finally, those all go together into the localization length, which is the figure of merit that's most important at the end of the day. It's an integrated figure of merit that takes into account the mobility, takes into account the wire quality, takes into account surface roughness, and so on. And you can see that the localization length here is in excess of a micron in the lowest subband. And so that tells us that it is actually large compared to that clean system coherence length that we've estimated. So these are very clean wires, and that's really like the first thing. In order to hit go, you have to have extremely clean, high quality wires. And this shows that we've accomplished that. Now, the second thing you have to do is you have to find the topological phase, because actually it's a fairly large phase space. You have a wire, it has a density that's controlled by voltage. There's a magnetic field. There are junctions that you're opening and closing. And so, if you want to identify the topological phase and tune up your device, that's a lot of phase space to explore. It's a bit of a chicken and egg problem. Ultimately, you might say, well, I'll know I'm in the topological phase when I measure some universal properties associated with the topological phase, but you're not going to, be able to measure them or even understand what you're doing unless you have some confidence that you're in the topological phase. And so that's a chicken and egg problem that we solved with something called the topological gap protocol. What you see here is what's called three-terminal transport data. So this is measuring local and non-local conductances. And this protocol basically takes this kind of data and identifies, with very high confidence where the topological phase is. It looks for certain signatures, and there are in principle, there are false positives that can occur where just because of where the impurities happen to be located in a given device, you might see very similar signatures just due to quote unquote luck. The topological gap protocol makes the hoops that the data has to jump through sufficiently stringent that it's very low probability of a false positive. You have to see, in particular, a phase transition, since you're going into another phase, the topological phase, where you see a gap closing and reopening. You have to see zero bias peaks at both ends of the wire, and it all has to be stable against perturbations. The question, of course, is how stable is stable enough, and that's what the statistical criteria is there for. And it depends, of course, on details of the device and the level of disorder. Here, that is actual data that I showed you up there on the top. That's actual measured experimental data. Here is an actual phase diagram from that device, in fact. It actually takes a much larger set of data than what I'm showing you there. Those are just some cuts through the data. And by looking for the stable zero bias peaks, looking for the gap closings and reopenings that define phase, that are signatures of phase transitions, and asking for the, requiring the requisite stability, you get here, the red is where the topological phase is, the blue where the trivial phase is, and the pale colors are where the system is essentially gapless, where you have, phase transitions, for instance. And you can see it's actually not that small of a topological phase. It extends over a Tesla in magnetic field and millivolt in voltage. So we've been able to obtain and measure devices with extremely clean devices that have topological phases that are, I would say, moderately robust. And as we've made our devices better, we've had a higher ratio of devices passing this protocol. Our Gen 1 materials, we measured around 71 wires, 18 of them passed the topological gap protocol. So, not a very high passing rate, but then we made some materials changes, some process changes, and the wires measured, of the 55 measured, 31 of them passed the TGP, and then Gen 2.5, we 13 out of 15 passed the TGP. And so as we've gone, made changes to design and changes to the process, and essentially made cleaner wires, we've had more and more of them passing the topological gap protocol. So more of them, a higher yield of devices with a topological phase. Okay. Now, in the topological phase, what's so special about it is that it has Majorana zero modes at the ends. And in particular, what's famous property of superconductors is that the electrons form Cooper pairs. Okay. And they really want to be in these pairs. There's actually a penalty for an unpaired electron because there's some electron that didn't find its partner. And so there's a strong even-odd effect in mesoscopic superconducting devices. In a topological superconductor, topological superconductors are actually don't penalize an odd number of electrons. They can actually accommodate in the superconducting condensate an odd number of electrons, and they do so by virtue of these Majorana zero modes, which are places where an electron can enter or leave, an unpaired electron can enter or leave the system and then join into the condensate. So, in fact, a topological superconductor has degenerate ground states of even and odd fermion parity, and that's what ultimately leads to H over E rather than H over 2E periodic quantum interference devices. Now, to make a qubit, kind of the standard qubit encoding is not based on a single wire with two Majorana zero modes, but instead on a pair of wires with four Majorana zero modes, connected usually by some kind of trivial, non-topological superconducting bridge, so that there's only there's only four Majorana zero modes. Now, this is the kind of device that we've made. How did we make that? It's again based on gate-defined nanowires. So here's a cross-section here. You can see it's again an indium arsenide quantum well. It's aluminum strips on the top surface. And then it's a couple of gate layers and dielectrics that are necessary in order to deplete the two-dimensional electron Gauss everywhere except underneath the aluminum wires. And then also to tune the density under the wires and to create some quantum dots that play an important role here. Okay, this is a top view of the device. You can see there's an H-like structure here. That H-like aluminum structure is the backbone of the device. Here's an SEM, or scanning electron micrograph image of our device. You can kind of see where the wires are in this image. You can see also the gates in the first and second gate layer. What they do are, here are the aluminum strips. There are two of them that are 3.5 microns long, 60 nanometer wide aluminum strips. Those will be our topological wires. We also have, what we often call an aluminum bridge. It's narrower. It's 40 nanometers wide and a micron long. And it extends, so that it extends to ground, so that the whole device is grounded. The reason that it's narrower is because when the two horizontal wires are in the lowest subband, and that's the subband in the transverse direction within the plane, when they're in the lowest subband, the aluminum bridge is fully depleted. And so it's truly a trivial superconductor. Underneath the aluminum, you can just forget about the semiconductor, and it's just like having an ordinary aluminum. Okay. Now we have some quantum dots for parity measurement. And the way that those quantum dots work is they couple to the parity in the wires, and by measuring the capacitance of these quantum dots, we're able to extract the parity of the electrons in the wires. Okay. So as I said earlier, it's 4 Majorana zero modes for a single qubit. So when this is tuned into the topological phase in the qubit configuration, there are Majorana zero modes at the corners of the H. Those Majorana zero modes are present when we're in the topological phase. This device that I'm showing you here, in fact, passed the topological gap protocol. You can see the phase diagram of the top wire in the top right. You can see the phase diagram of the bottom wire in the bottom right. And there's a magnetic field. We can tune the density on each of those separately. We tune through those plunger gate voltages. We can actually also tune the magnetic field, but we have only one magnetic field for the whole device. And the good thing is a single magnetic field enables you to be in the topological phase on both wires. Okay. Now, the qubit again is fixed total parity. So if I say, hey, what is the total parity of this? Let's say it's all even. Okay, so an even number of electrons in the device. Well, the way I can get that is I can have both wires can have even parity or both wires can have odd parity. So like even, and odd, odd. In equations, in terms of the Majorana zero modes, we'd say that I gamma 1, gamma 2, which are the Majorana operators on the two wires, that's equal to I gamma 3, gamma 4, and it's equal to plus or minus 1. Plus 1 is even parity, minus 1 is odd parity. Okay. Now, the quantum dots that we have here, what they enable is electrons can tunnel from the zero modes to the dots and back. That has an effect on the capacitance of the quantum dots, and enables us to measure the parity. Okay, so here's the Z measurement, okay? Measurement of the parity on a single wire. It's how we measure the fermion parity of the bottom topological wire. In terms of a qubit, it's like measuring Z, okay? And, when we do this measurement, what do we see? So I should also say there's also an X measurement. So the X measurement doesn't commute with the Z measurement. It's a measurement of Majorana zero modes on two different topological wires. And you can see these are both interferometers. There's an interferometer that takes a quantum dot and a single wire, and it's an interference loop just connecting those two. There's a different interferometer here, which actually bridges the two wires, okay? Now notice the X measurement is performed natively here. Okay, we just do a single measurement. It's just a measurement of the capacitance on a different quantum dot. What we don't do is we don't actually do a circuit. In most other qubit platforms, the way that you would do an X measurement is, in fact, you would do a Hadamard gate and then a Z measurement. Okay, but that's not what we do here. An X measurement is just a native operation. And in fact, ZZ and XX will also be performed natively, not via some circuit with ancillas, which is the normal way to do it. And that's extremely useful because those are the kinds of operations we need for quantum error correction. So important point here is we can natively do many more kinds of measurements than you can ordinarily do, and those are in fact topologically protected measurements, and it's the measurements we need for quantum error correction. Okay, now let's take a look at the X measurement. Well, the X measurement, it's a fermion parity measurement. Okay, both wires are in the topological phase, or it's qubit configuration, and X is I gamma 1, gamma 3. Okay, and we're doing a measurement. It's coupling the two wires. When we do this measurement, we measure the capacitance on that dot, which is this dot over here. Here's what we see. First of all, we see that it's flux dependent. Okay, this is what you'd expect. It has a flux dependence that agrees with what we'd expect for this area. Actually, the lithographic area here, is about 1.75 microns squared. And we see a periodicity associated with that. What I'm showing you here is a kurtosis. So kurtosis is a statistical measure of a distribution that is basically measuring non-Gaussianity. Or this is actually often called the excess kurtosis. So the excess kurtosis is 0 when you have a Gaussian distribution, and it's negative when you have something that's broader than a Gaussian distribution, such as, for instance, a bimodal distribution or multimodal distribution. Okay. So as we'll see, this is a sign that we have bimodality and that the bimodality is in fact flux dependent. Okay. So that's really a good thing because it's showing we are actually measuring an interference phenomenon. And what's so significant about that is actually this middle wire here, this bridge, in fact, is fully gapped. It's ordinary aluminum. Individual electrons should not be able to go through this. So the fact that we're able to see an interference measurement is telling you that something interesting is really happening here. Okay. Now, when we sit at one of those points, so if you look here at this blue dashed line, a place where the kurtosis is quite negative, then if we just monitor the state of the system, you can see that there is a telegraph signal here, that the capacitance is bouncing up and down. And this over here is a zoom in of this piece here, where it's very clear that it's a telegraph signal. It's bouncing between two values. If you look at a histogram of measured values, what you see is it's clearly bimodal. So that explains why the excess kurtosis was negative. We have a bimodal distribution, and we interpret that as the two parities that you could measure in an X measurement. And we can see that there's some switching occurring between them. On the other hand, if we go to this dashed line over here, then you can see that actually there really isn't that bimodality, or at least there isn't an apparent bimodality. You look at this and you zoom in, it just looks like noise. Now, in fact, that looks like a single Gaussian, but it actually could fit a superposition of two Gaussians that are very close together. So there isn't a clear bimodality here, okay? At the very least, and there's nothing that looks like a clear telegraph signal. So there's an h over 2e periodicity as expected for quantum interference effect, and it actually has basically the bimodality that we expect, okay? What is the time scale associated with these switches? Well, if we take the autocorrelation function, you can see the autocorrelation function has a clear exponential decay. That exponential decay has a time constant associated with it of around 15 microseconds. So what we're seeing is switching back and forth between two states on a 15 microsecond time scale. So I go back to this, 15 microseconds is the typical dwell time in either the upper or lower state here, okay? That's what this is telling us. On the other hand, if we're sitting at the place where the bimodality is not apparent, it really just looks like noise. There is a peak here, right here at 0. That peak at 0 is uncorrelated readout noise. We believe that that's primarily due to actually the amplifier in our readout chain. And then everything else just looks like background out here. So there's not much structure here away from the points where the kurtosis is large, which are flux periodic. And in the places where the kurtosis is quite negative, we see a clear exponential decay with a 15 microsecond time scale. Okay, so that's great because that's not that short of a time scale. What happens when we do the Z measurement? Well, in the Z measurement, that's also a fermion parity measurement. It's a measurement of the fermion parity on the bottom wire over here. Okay, and when we measure the fermion parity on the bottom wire, what do we see? Well, we see, again, switches. So we see jumps in the capacitance, but the time scale is much longer. If you look here on this axis here, the switching time is actually 15 milliseconds. So it's a much longer, much slower time scale, a much longer time scale, okay? And this is in fact similar to, a parity observation we did in a simpler device. So we have a simpler device where we first started developing these kinds of capacitive parity measurements. And in that simpler device, we actually saw a similar time scale. Actually, it was more like 2 milliseconds there. So we've gotten around an order of magnitude improvement, which we think is due primarily to improvements to the shielding and filtering. And I'll explain why that's critical for this kind of process. So, to summarize, we're seeing two very different time scales, two different error rates. That's what these switches are. They're errors in the X or Z measurement. Or I should say they're errors in the idle state during measure or in the measurement configuration where it switches from, X equals +1 to -1 or Z equals +1 to -1. Okay. How do we think about this? Well, one way to think about these two very different time scales is we have two very distinct measurement bases, X and Z measurements. And the Z measurement is actually dominated by leakage processes. So a quasiparticle is excited, maybe from ground, single unpaired quasiparticle. We think that that's due primarily by infrared radiation that leaks into our system. We control that and suppress it as best we can by shielding and filtering. We actually can make it worse by injecting quasiparticles intentionally, and we've checked that. So we think that's a dominant process. The time scale is about 15 milliseconds, actually makes sense. That corresponds to about less than 1, maybe 1 or 0.1 quasiparticles per micron cubed. Okay, which is it's a good but not absolutely state-of-the-art number. So it means we're doing something right in terms of shielding and filtering, but we've not really, I would say, pushed the state-of-the-art there. And it already gives us a very, pretty long time scale, 15 milliseconds. On the other hand, there could also be Pauli errors. Those Pauli errors would be, for instance, exchanging a fermion from the top wire to the bottom wire. They're exponentially suppressed by the aluminum gap over the temperature or the wire length divided by the aluminum coherence length. And the aluminum gap and the aluminum coherence length is because this, the bridge or backbone, the semiconductor is fully depleted there. It is just aluminum. And that has a short coherence length, a relatively large gap. And So, that's very strongly suppressed, which is why we don't really see those processes. We don't see those kinds of palette processes. What we see is this 15 millisecond time scale. We estimate based on the known gap, temperature, coherence length, that this is a very long time. On the other hand, in the X measurement, those errors, when we measure I gamma 1, gamma 3, that suffers from errors, for instance, if a fermion is exchanged from the left side to the right side of the device. And when that occurs, the only thing that suppresses, or the thing that suppresses it, is the topological gap, okay, relative to the temperature, or the topological superconducting coherence length relative to the wire length, okay? And the topological gap is much smaller than the aluminum gap. The topological superconducting coherence length is much longer. Just to give you a sense, the aluminum gap is what, it is, probably around 200 microvolts, and the topological gap around 30 microvolts. So it's really almost an order of magnitude sitting inside of an exponential. And so this is not a negligible process, these kinds of Pauli errors in the X measurement. And actually, our estimate is we do expect timescales of around 15 microseconds. So there is 3 orders of magnitude. It's very asymmetric error rates, but in our model, this is it's not surprising within our model, because one of these error rates is strong. The Pauli errors are very strongly suppressed by the aluminum gap and aluminum coherence length, and so therefore it's non-equilibrium quasi-particles, which are controlled by shielding and filtering. And on the other hand, it's the topological gap and topological coherence length, which are significantly smaller. Pictorially, certain types of errors would have to tunnel under or be thermally excited over the aluminum gap, and the others only have to deal with the topological gap. Okay. So, where are we? Where does this put us? Well, in terms of our roadmap, there are, 2 directions to go. One is, direction of device complexity. As we go down a roadmap, we are making devices more complex. We started with a single wire. We developed the parity readout on 2 parallel wires. I just showed you our scalable qubit architecture, which has 2 non-collinear wires with a bridge between them. We have actually an 8-qubit. We have multi-qubit devices, and then in the long run, we're going to be looking at devices with hundreds of qubits, to make up logical qubits. But at the same time, as we go through device complexity, we also need to improve the qubit specs. The number one lever for us is the topological gap, okay, the size of the gap in the topological phase. But there are related things like the yield, which is the fraction of devices that actually have a topological phase, or that work in some sense. The wire length, because the coherence length is compared to the length of the wire. So, if we can make high quality wires that are longer, that's helpful. The stability of the device, and very importantly, the signal to noise ratio in the types of measurements that I discussed, these capacitance measurements. And what you can see is that over time so far, we've made some improvements. We've gone to somewhat longer wires from 3 micron to 3.5 micron. We've improved the median size of the topological gap from 30 to 40. In the long run, we need to get to 70 and then 110. The yield that we've seen of around, started out at 50%, is now above 50%. And then eventually we went to above 50%, and now is above 75%. So we've gotten these improvements through improvements in the materials, and we will be continuing down that path as we consider device complexity. So we don't plan to build a topological quantum computer with devices that have a gap of 30 microvolts. That is too small. 30 even 40 microvolts. Our next target is 70, and then ultimately over 100. And then those are devices that are going to have a lot of stability and protection against errors. So here are SEM images of some of these devices, the single wire, the 2 collinear wires, the qubit I just showed you. And then you can see what an 8-qubit and more complex multi-qubit devices look like, the gates and the routing you can see there. So, let me take this, this opportunity to acknowledge the work of all of the co-authors on these papers. So this is, the 2023 paper that we published, where we really had first seen the topological phase, or first passed the topological gap protocol, which gave us very high confidence that we were in the topological phase. And the reason there's a lot of co-authors on this paper is because this depended on molecular beam epitaxy growth advances fabrication advances, advances in the measurements and like the 3-terminal protocol measurements, simulation and design. All of our devices are simulated extensively and optimized through simulation before they're fabricated. And then on the data analysis side associated with the protocol, it's then based on the parity, the interferometric parity measurements that I mentioned to you again, which rely on all of the growth, fabrication, design, measurement, and so on. But then on top of it, a significant amount of system design. It's more than just the device. As I mentioned, the shielding and filtering are critical for suppressing quasi-particle poisoning, but also the signal to noise ratio on the readout. The better the SNR, the faster and more accurately we can do the measurement, and that in turn is controlled to a large extent by the amplifiers in the readout chain. And then the work that I just told you about on our qubit, we'll be posting something on the archive relatively soon, so keep an eye out for that. So with that, let me take some questions.
Hello, I'm Bhupan Dev from this center. Two questions.
Yes.
First of all, the cross-sectional TEM picture that you showed, the indium arsenide looked very nice, but aluminum, is that single crystalline or is that at all single crystalline?
Yeah, so it's a good question. Let me show you the cross-sectional TEM. So so it's an indium arsenide quantum well. The top barrier is indium aluminum arsenide. This is about 6 nanometers of 12% aluminum, indium aluminum arsenide. So you can see it's very well crystalline. Here's the aluminum. You can see it's also quite crystalline. What you see up here at the top is the oxide. So we oxidize the aluminum, which stabilizes it. So because otherwise aluminum would tend to de-wet and ball up and you get droplets. So we stabilize the wire by oxidation, and you can see some oxide forms up here, a few nanometers up on the top.
Is that aluminum oxide?
This is aluminum oxide on top, correct.
Okay, but aluminum crystallinity is not quite clear though.
I don't know. Can you see this? It actually is. I think it's quite clear on this length scale. Okay, that the aluminum. Can you see my cursor?
Mm-hmm.
Yeah. So if you look clearly, the bright spots are the aluminum atoms. It is quite crystalline. However, it is not a single crystal. The grain size is somewhere between 50 to 100 nanometers, but the grains the different grains are very low angle, between them. So they are rotated relative to each other, but by a very small angle on the order of only about a degree or so. So it's not a single crystal. It is polycrystalline, but the grain size is 50 to 100 nanometers, and the different grains are only slightly rotated relative to each other. On the scale that you see within this field of view, it actually does. If you just count the bright spots here, it looks crystalline, but as I said, it's actually polycrystalline.
Okay, my second question is on the topological phase. Mm-hmm. How did you check the stability against perturbation?
Great. So So the way we check stability against perturbation is, so this is, what you see up here is, actually, I'm going to go back here. This is transport data. So what we're looking at here is the differential conductance, DIDV over here. So, this is a wire with 2 ends. This is DIDV at one junction. There's similar data for the other side of the wire. What you're looking at here is a non-local conductance, so it's a derivative of the current at one junction with respect to the bias voltage at the other junction, and vice versa. So this one is sensitive to it's basically a measure of the density of states. When the junction is in the tunneling regime, it's the density of states at that end of the wire. This is actually sensitive to bulk states in the nanowire that are between the induced gap and the parent gap of the aluminum. And so the way we check for stability against perturbations is we open and close the junction. So the junction transparencies vary between around 0.2 times E squared over H to around 1 times E squared over H. So we vary the junction transparencies, and we require some features like, this zero bias peak here. We demand that it be stable against variation changes in the junction transparency. We also, so that's sort of stability with respect to local perturbations, in the device. But then we also require it to be stable against, changing the magnetic field. So, if you look at this topological phase, these, this red is a region where you have stable zero bias peaks. By stable, again, I mean with respect to changing the junction, opening and closing the junction more. And you can see it's persisting over almost a Tesla in magnetic, actually a little more than a Tesla in magnetic field between here and here. We similarly also, require stability with respect to change of density, which is the voltage. And then the same thing has to hold true for the gap close. So you see there's a gap closing and reopening here. The gap has to exceed, a value which is, determined by the noise in our measurement. So, around 10 micro EV. So the gap has to be more than 100 millikelvin. But then also the boundary of the phase has to be gapless over, most of its boundaries. So it is stability with respect to opening and closing the junction, stability with respect to changing the density in the wire, stability with respect to magnetic field. Now you can ask, well, how stable is enough? Is 1 Tesla enough? Does it have to be stable over 2 Tesla? Does it have to be stable over 1 millivolt or 2 millivolts in plunger voltage? And the answer is, for the device that we have, for the level of disorder that we have, we know that you can accidentally have some zero bias peaks or gap closings, and they could accidentally be fairly stable, just, because there's no, it's a superconducting system with strong spin orbit coupling and broken time reversal symmetry. So you can have zero bias peaks. But for these values of disorder and materials parameters, the probability of something, which we determine through simulations, we simulate many, many disorder realizations. The probability of seeing something like this is very small. So, the false discovery rate is at, really like 5% at most. So when we see something that passes this protocol and has that level of stability, it's very unlikely to be kind of accidental.
Okay, I think the next question is the Z operation and X operation. So one is controlled by both of them are controlled by length of the wire, but one of them is said that Z is by the aluminum gap, and the other one, X operation, is by the topological superconducting gap. And how much are the different?
Yeah. So what you see in the Z measurement is, so for the Pauli errors in particular, you have to exchange fermion parity, or there has to be some, there has to be something exchanged either through tunneling or through thermal excitation between this Majorana zero mode and this one. So that, such a excitation has to cross this bridge. Okay. So yes, it has to cross half of the wire here and half the wire here where the topological gap holds. But there's also a segment here. So there's a length in this direction and there's length in this direction. What's really critical here is the length in this direction. And here it's the aluminum gap. So this length of this wire is 1 micron, but the coherence length is only 100 nanometers here. Okay. And the temperature in this device is around 50 millikelvin, but here the gap is, is 2 Kelvin. So it's because you have to cross from one wire to the other via this trivial bridge, which is actually shorter than the wire here. This direction, it's 3.5 microns. Here it's only 1 micron, but the aluminum gap is so much larger and the aluminum coherence length so much shorter. Here, to go from the left side to the right side, you don't have to cross this bridge. I mean, there are processes that do, which go here and then come down, but you don't have to cross the bridge. You can go entirely on one of the wires. Those wires are 3.5 microns long, but the gap is much smaller and the coherence length much longer. So the gap is, is 30 micro EV here, and the coherence length is, 1 micron. So, so that's why it's just much less of a suppression here.
Okay, thank you. The next question is that the other approach, like the magnetic atomic chain on superconductor, That's another approach towards topological superconductor, topological. So what's the current status of that?
I don't know. I haven't been working very closely on that, so I couldn't tell you very much about it.
There are some people like Professor Wiesendanger in Hamburg has been working on that extensively.
Yeah. So again, that's not the approach we've taken. I haven't followed that too closely. Our approach, we wanted to have a path to large gaps, large controllable energy scales, ability to make fairly long wires, and to read out joint parity quickly and accurately. So that's why we went down the road that we went down. But I can't tell you too much about alternative approaches.
Okay, thank you very much, and for the nice presentation. Now, mine is over. Are there any online questions? How will we see? Can we see anything in chat? Okay, so I mean, one question that I may wish to ask is that what is the time scale to have say 2 qubits in your system?
What is, sorry, can you say again, what is that?
As of now, you have 1 qubit, right, where you are applying this measurement. So time scale for 2 qubits where you can apply say C0 gate and all that.
Yeah. So yeah. Let me good. Let me say a little bit more about that. Yeah, good. Can you see my screen? So, this is a schematic of what a 2 qubit system looks like. And I actually showed you an SEM. If you recall, I showed an SEM actually of an 8 qubit device. So this is looking at just a piece of that 8 qubit device very schematically. Here's one of the qubits similar to what I showed you with the 4 Majorana zero modes. And here are the two of them next to each other. What we do is, again, we do sequences of measurements. So we don't actually ever do a C0 gate particularly, but we can do what we actually do is we do a 2 qubit measurement like an XX or a ZZ measurement. And here's an XX measurement, the way it works. So this is a Y measurement. Here's what an XX measurement looks like. There are quantum dots up here. And we again measure the change in the capacitance of one of these quantum dots. Right now these measurements, they're pretty accurate on the few microsecond, time scale. 5 to 30 microseconds is sort of optimal SNR. Actually, we believe for 2 qubit measurements, we can get similar SNR. So, the speed at which we can do these measurements is again comparable. So, in the, let's call it around 10 microsecond scale, long run, we want to be able to do all these things in around a microsecond. But, that's going to require some improvements on the system side with the amplifiers and reducing parasitic capacitances. But, right now we're in that, roughly, I would call it 10 microsecond time scale for these kinds of measurements. But for that measurement, your time scale is in millisecond, right? So no, so actually no. So if you go back and take a look at the Z measurement, 15 milliseconds is actually the error rate. So we can actually do this measurement is very accurate in around tens of microseconds. Okay. On the 15 millisecond time scale, that's the time scale on which errors occur. So the time scale on which we do measurements, which in our basic operation is measurements, is much shorter than the time scale for errors.
Okay. So when can we expect to have a functioning 2 qubit quantum computer based on topological qubit?
We're working on it right now. Stay tuned.
Oh, okay. I mean, there was some skepticism from what I heard, whether it is a functioning 2 qubit quantum computer or not.
Yep, stay tuned. I mean, what I showed here, I think is, let me go here. Here's one of our devices that this has 8 qubits actually. It's an 8 qubit device. We have devices like this in testing. They're not fully characterized or benchmarked yet, but that's ongoing work.
Okay, so this 8 qubit array, I mean, is it already there, or I mean,
Yeah,
you
this is an SEM image. This is an SEM image. You're looking at it. This is not a schematic. This is an actual device. All of these are scanning electron micrograph images of existing devices.
Oh, okay. Thank you.
Mhm.
Anybody wishes to ask questions? Okay. So I think
I have a question.
Oh, yeah, sure.
Yeah. So, well, I mean, my question is a bit futuristic, but I presume you've thought about this. That is, what kind of problems you think for which it is possible to achieve quantum advantage using a topological quantum computer of the type that you envisage to build? Is it, I mean, all problems across the board, or there's some selective problems?
Well, I think the most natural thing is actually the thing that Feynman, was first motivated by when he started thinking about quantum computers, which is, if you want to simulate a quantum system, it's very hard to do with a classical computer because of how large Hilbert space is. And so quantum computers are very natural because if you want to, let's say, simulate a molecule with a few hundred orbitals, that's, very, very difficult to do with high accuracy classically, unless you know that only a very small subset of those orbitals get occupied, or very low entanglement. So, those kinds of problems, finding ground states of large molecules and reaction pathways for large molecules. For instance, anything involving transition metals, which is typical catalysts for a number of chemical reactions, and also some of the most interesting materials, whether it's superconductors or magnets, often also involves, similar highly quantum, problems on that time scale that's just beyond what you could do classically, where maybe you could hope to simulate 50 qubits or something like that. But if it's 100 or a few hundred, there's no hope. And so I think those are kind of I mean, obviously, we'll learn other things that a quantum computer will be good for when we start playing around with one. But the first thing I'd be interested in is to, solve chemistry and materials problems that are just beyond the reach of classical simulation.
Well, I agree with that. I mean, but that's true of, I mean, in principle, that's true of any quantum computer. But specifically for a topological quantum computer, is it similar to, the choice of problems? Is it similar to other quantum computers, or are there any specific class or classes of problems for which a topological quantum computer would be better suited?
Well, I think once you get to the logical qubits, you're at a level of abstraction that you can abstract away any of the underlying physics, or whether it comes from topological qubits or anything else. At the point of logical qubits, it's just logical qubits and logical operations, and you probably don't care where they came from. Now, right? So I think that it's going to be the same applications. Now, there may be an intermediate regime where either you have a few logical qubits, or maybe there's error correction, but not quite logical qubits. And in that intermediate regime, it may make a difference whether you have topological qubits or some other kind of qubit, just because of potentially, the connectivity of your device, or, like what I mentioned, the asymmetry of error rates, that some things may be, much more accurate than other things. So I think there may be, in that intermediate regime, something a little bit different about the types of applications, but that's, I would say, that hasn't been the highest priority to kind of figure out what those are. our focus is very much about kind of the really big, big important problems we want to solve with an at-scale quantum computer.
Okay, thank you.
Okay, so if there are no more questions, I think, let's thank Professor Nayak for taking this trouble. Because it is, I think, late in the night in US. So thank you very much for this very illuminating talk and taking this trouble to give this talk so late in the night. So thank you very much.
My pleasure. Thank you very much. Appreciate the questions. Bye-bye.